All right, so we're talking today about the derivation that proves that endo and exothermic reactions will change the equilibrium constant if temperature changes. What that really means is that KEQ, all right, is temperature sensitive. Now, let's just dive into what I'm talking about. Let's talk about a reaction here, all right? And let's just start with the reaction. And I'm going to use a nice color here. And let's say we start with a reaction like this. We can do this. A plus B gives me AB. And it doesn't really matter what the chemicals are, but let's make this forward reaction, okay, exothermic. So we would put the heat here. And we should all know an exothermic reaction, energy is lost. Okay, the change of delta H, okay, is negative, meaning there's a loss of energy from the product, from the reactants to the products, of potential energy. We should all know that, but here's what I'm talking about. If we talk about a basic Le Chatelier's principle question, and we say, hey, okay, in Le Chatelier's principle, if this reaction is at equilibrium, okay, or is a reversible reaction, and let's pretend I decrease the temperature. All right, if I decrease the temperature, I always say to my students that this is the stress that we provided. All right, and of course the reaction responds accordingly to regain its balance. So this is the stress, what we do. In this case, I'm saying temperature drops, and the response is that you teach your students, you've seen this before, that hey, the temperature increases. And so how would we do that? Well, we would say that the shift in the reaction would shift to increase, and we would say that the reaction shifts to the right. And in truth, it does. There is an increase in the formation of the what? Products, and there's a decrease in the amount of reactants. That is what we see. We know that a decrease in temperature always favors an exothermic reaction. What else do we know? And we can memorize this. Let's write this reaction the other way. Let's take AB, okay, and this would be a decomposition reaction, break apart into A and B, okay, and where would we put that heat? I guess I have to move this. All right, so here I'm just going to move it, and I'll move this over here because I forgot to think about where the heat would go, and back to here. And so what do I have? I would have the heat right here. You notice I'm just going in reverse, okay? And of course the delta H of this reaction would be positive. It's exothermic in this direction. Hey, it's going to be what? It's going to be endothermic in the reverse. Okay, so I just kind of rewrote this. All right, now what do we know about an endothermic process? Well, here's what we know. We know that when the stress, if it's endothermic, now we've just changed the situation. Now the heat is on the reactant side, meaning A and B require an overall absorption of heat for the reaction to go. It's an endothermic process. The temperature of the surroundings decrease. Okay, now here's the stress. We're going to increase the temperature. What's the response by the reaction? The response is to decrease the temperature. And how do you do that? You've been told that, hey, if we have too much temperature, this reaction is going to shift to the right to lower the heat. The heat would be lowered, so would AB, because you're going to use it up to make an A and B would increase. Now we've learned that these supposal shifts are really due to saying that in this case, this arrow on top here is getting more spontaneous, or the direction to the heat is getting more spontaneous as we decrease the temperature. We are favoring the exothermic way. And guess what? As we do what? Decrease the temperature for now an endothermic reaction, we would favor the endothermic way. Okay, so if I was to do this in the same reaction, and I tried to make this clear, if you decrease the temperature, we would favor the what? The exothermic way. Having the heat here makes these are the reactants and these are the products. The AB is the products, okay, clearly. Now, if we now increase the temperature with the same reaction as written right here, hey, now the reaction's going to favor the endothermic way, which is the reverse. Okay, that is something you need to know. Now you can memorize that, okay, but you can understand it. And what I want to tell you is that the reactions really do not shift in terms of Q. They shift in terms of KEQ. So let's just go to the derivation to prove this, okay? Now I'm going to start with the endothermic process here. And I'm going to draw a U diagram, okay? You get it, hopefully. Now, this helps us understand. I'm going to pretend that the equilibrium is favoring the reactant. So here I've got this diagram, and I'm coming up here. And what this means is this position, okay, is going to be KEQ. That's the death of the reaction. And we know that reactions always move toward equilibrium. Right here is going to be 100% reactants. That would, of course, be A and B. And then, of course, this is 100%, 100, that's terribly drawn, 100% products, okay, at this position. This position's here. And that, of course, is going to be what? A and B. Okay. Now, why do we have a shift? Everything we've learned so far is because, well, Q versus K, EQ. And when we change concentrations of reactants or products that's different from the concentrations when they're static, we know that Q can be different than K. But what happens here is KQ changes with temperature. So let's go to this beautiful derivation. All right, so what do we know? We know that delta G standard conditions is equal to delta H minus T delta S. And what else do we know? We know that delta G standard is equal to, from another derivation, okay, well, by the way, this is because of constant pressure and constant temperature. It's a beautiful way for us to identify the universe's enthalpy change overall by looking at system quantities. This one we've got from deriving the non-standard delta G, but in any case, we're jumping here. Delta G is equal to minus RT ln of K. Okay, now those are two formulas for delta G. Okay, so there they are. And so what we're going to do is we're going to, okay, set them equal. All right, let's set them equal and see what we got. I'm done with this color, so let's go here. So I'm going to start here. So we're going to go delta H minus T delta S is equal to negative RT natural log of K. The whole point of this is I want to see how the equilibrium constant relates to changes in temperature if we have different enthalpies here. Okay, so we're going to solve for ln of K. So ln of K, or the natural log of K, becomes delta H minus T delta S, and we're going to divide by this expression, negative RT. Okay, all right, now let's go further. All right, now we're going to simplify this because mathematically, what do we know? We know that delta H over negative RT, this is minus T delta S here. So this is also minus, mathematically, it's also T delta S over, all right, negative RT as well. That's mathematically this expression here, all right, this expression here mathematically is the same as this one. Okay, now let's continue writing our little hearts away, and we equal what? Ln of K. All right, now natural log of K. We got some things we can cancel, so let's do that. And we can cancel our temperature here and here. All right, and you notice negative over negative makes a what? A positive. So let's rewrite this now. Okay, and clean this up as we simplify. All right, so what we have is delta H over negative RT is plus, right? Plus delta S over R, okay, it's plus this expression, so this is positive, okay, equals the natural log of K, EQ. That's our beautiful formula here. Now we're going to manipulate this, okay? We're going to manipulate this. How do we do that? Well, we're going to talk about the what? We're going to talk about the endothermic process. And what do we know about the endothermic process is, hey, what favors an endothermic? Hey, you increase the temperature, we decrease the temperature by the reaction shifting forward. So let's see if we can prove that. So let's talk about endothermic. So it's getting back to here. Okay, so let's go make this green. And so this expression here, if it's endothermic, you should know it's positive. Okay, and we're also talking about temperature increasing. All right, so what do we got here? If it's endothermic, party people, is what we have is we've got a negative value here because we got this negative sign. Negative and positive, positive divided by a negative, positive divided by this negative is going to give me an overall negative value. Now, if I increase the temperature right here, what's that going to do? That's going to make this negative number become a smaller negative number. As you make the denominator bigger, this expression equals a smaller negative number. And this smaller negative number in this box is being added to this positive value. So what's happening is that you're adding a smaller negative number to this than it was originally, which means your K EQ or K is getting more positive. And now you need to know, if you've got a greater or more positive K, what is K? KQ is the concentrations of the products over the reactants. Coefficients become exponents. Solids and liquids do not matter. But if K is becoming more positive, that means we're favoring more products. Hey, if it's endothermic and temperature is going up, what we're saying, party people, is that the equilibrium position is going to change. And so we have a brand new equilibrium position, and it's now going to move here forward. And now this will look like this. Whoops, swoops down and comes up. We're going to favor more products. Remember, this is 100% products. So the KQ just changed position. Now, party people, if I was at this position, right, it means what? Q equals K at this position. And all of a sudden, I changed the value of KQ. Now what I have is I have a Q that's not equal to K, and it's what? It's less than K. And what we learn, we always move toward what? Equilibrium. So the forward reaction is now going to be more spontaneous. And that makes sense. If you're going to make more products, okay, and the equilibrium goes forward, becomes what? More positive, then the reaction is going to be more spontaneous. And that's why we say there's a shift, okay, to the left if you're endothermic and temperature increases. We always favor the endothermic way because we're going to favor the chemicals that are on the opposite side of the heat. In this case, we call it the products. All right. But as I said, it gets kind of confusing because if it's endothermic this way, all right, we favor the endothermic. What were the products over here? A and B. So if I have a reaction that's exothermic, the reverse, it's written exothermically in the forward like I have here, right here, okay, then what's happening is if I do what? If I increase the temperature, I'm going to favor the reverse reaction, which does what? Increases A, increases B, and that's what I'm showing, okay, right here. So we prove that, okay? We prove that by this very, very clean derivation. Okay, well, we can't do one without the other. Let's do the derivation for exothermic. So let's go back to here, and what we have down here is what? We had delta H, I can do this, okay, over negative RT, this is just a simplified, plus delta S over R. And that equals the natural log of K. Okay, party people. Now I'm going to do an exothermic. And I know it's kind of confusing because we're going backwards and forward, but I'm going to deal with this reaction right here. The one that's written on top, right here. So this is the exothermic. And what I'm going to do is I'm going to decrease, okay, I'm going to decrease like we did over here, right? I'm going to decrease the temperature, okay? And we're going to see that there's going to be an increase in temperature by favoring the exothermic wave. So we should see AB being favored if I decrease the temperature. If it's exothermic, delta H being negative, let's go after it. All right, so here we go. So now let's get a different color here to contrast. I'm going to go with whatever like this is. And now, so this value is negative because it is exothermic. Okay, now notice a negative divided by negative makes this an entire expression, okay, equal a what? A positive value. Okay, now what's the stress? Well, the stress when it comes to delta H and what it follows, we know that exothermic reactions are favored when temperature drops. Let's see if we can prove that. Temperature drops means we're going to make more heat, so we favor the production of heat. That's how this works. Any case, so what am I doing at a positive value? Okay, and so what's happening here is I am going to have a positive value, and because the denominator, okay, is decreasing, what's happening is this entire expression right here is becoming a bigger positive value. And this bigger positive value is going to now be what? It's now going to be added to, all right, this positive value. So which means the ln of K becomes what? A greater than 1 or more positive. Now, if it's more positive, it's going to favor the what? It's going to favor the products. Now, this gets confusing because you say, well, wait a minute, it just went forward. But wait a minute. If I look at this U diagram here, where I was using this reaction, this one up top, where it's endothermic in the forward, isn't it exothermic in the reverse? So in the reverse, this is the product. So if these are the products going in the reverse, I'm going to favor now these are the products, and K is going to what? Favor more products. So the K is going to what? Move in this direction and favor more of my products, which are A and B. Okay? And therefore, what's going to happen is this thing is going to change and find a new what? K position right here, KEQ. Favoring, now it's no longer the reactants if I'm moving in reverse. This is the reactants, this is the products, and K gets bigger, which really means we favor the products. The products are now on this side, and the KQ changes. And what happens? If I was at this position and Q equals what? K, and all of a sudden what? I've just moved my equilibrium constant because temperature changed. Now I'm where? Hey, I'm right here. And now Q is what? Too big for K, bigger than K. And what's going to happen is I'm going to move in this direction in the reverse. And we're going to what? Favor the formation of AB and release more heat when temperature drops for an exothermic reaction. So that just proves everything. And what you need to know, again, very simply, okay, and it's a lot of stuff going on here, but if you're dealing with a exothermic process, which is the top one, heat's on the product side, if you decrease the temperature, you favor the formation of more heat. You follow the exothermic way. If you have an endothermic reaction, hey, you're absorbing heat and you increase the temperature, you'll favor the what? You'll favor the endothermic way, the way you wrote it. Okay, so again, that's to show you that equilibrium constants are temperature sensitive. You change the temperature. So when you do Le Chatelier's principle for temperature, are you really shifting the reaction? Well, you're shifting it, but because you're what? You're changing the what? The equilibrium constant here. That's what you're changing. You're changing the equilibrium position. And then, of course, Q changes with relation to that. All right, so hopefully that sheds some light on this. All right, have a great day.